Good afternoon, everyone. So I'll first thank the organizers, including myself, for giving me this opportunity to present my work. So the title of the talk is Tavis Cummings Dimer, Chaos, Ergodicity, Integrability, and Imbalance. This is an ongoing project, which I've been working on with Manas and David. Before going on to the motivation of the talk, I'll give a brief overview of like what questions are we asking. So first of all, there are two different physical phenomena that we're looking at. One is localization, delocalization, and then there is integrability and chaos. And we're looking at these phenomena in this model of Tavis Cummings diamond, which I'll come to. And we are asking questions like, can we establish some sort of link between these two distinct phenomena? And not only that, when we are talking about this quantum model called the Tavis Cummings dimer, it also allows a nice classical version, which in itself is has a very rich physics. And so we are going to look at both these quantum and classical versions of the model. And so when we are looking at localization, delocalization, in the quantum case, we use exact diagonalization. In the classical case, we use Hamilton's equation. And when we're talking about chaos and integrability, in the classical case, we use the well-known method of Lyapunov exponents. And like yesterday, Shreyas mentioned that what do we do for when we want to investigate chaos and in quantum models? I mean, one prescription is finding out OTOCs, but I'll be using some other description, some other diagnostic tool, which is based on random matrix theory. And then on top of that, we are also asking questions like, can we establish some kind of correspondence between this classical and quantum version, especially in the context of localization, delocalization physics. So now that you know that what we are working on, like so what basically motivated such questions is that, first of all, localization, delocalization physics is an active area of research, and it's very interesting, especially in fields of cavity QED, quantum optics, etc. And it's a phenomenon that's observed both theoretically and experimentally. And I've been working with Manas on this for a while now, and it's also relevant to quantum computations and simulations. And then there comes this picture of integrability and chaos. Now, I don't need to tell you about why chaos is important. Enough has been said about it, especially in this event itself. But on top of that, we see transitions from integrability to chaos in cavity QED models. Even this Tavis Cummings dimer allows such transitions, and such transitions are always very interesting to study theoretically. Okay, now coming to the model. So we have this, the Tavis Cummings model is basically a bunch of two-level systems which do not interact with each other, but they interact with a single mode radiation field, which is given by this term in the Hamiltonian, which is some oscillator. And then all these spins, they don't interact with each other, so we can take some large spin operator, say omega s sigma sz. And this is the interaction term, how the radiation field acts with the spins. And we're looking at this Hamiltonian, you can convince yourself that this has a conservation of total excitations. And what we do is we take two such systems and we couple them together with this kind of a kinetic coupling term. We have a left and a right system. And one thing that I should point out, that these systems individually are integrable, but when you dimerize them, when you take a dimer, you can reach places where this integrability breaks. Okay, so when we're studying imbalance, what I mean by imbalance is we put some excitations in one of the dimers, one of the monomers, and we let the system evolve. And the difference between the number of excitations between the left and the right is what I define as imbalance, which is quantified by this quantity here. And what we do is we put all the excitations in the left monomer, and then we evolve the system. And this is imbalance plotted as a function of time. And we see for lambda equals 10 J, it's like large interaction strength, the imbalance remains to be some positive value, and which indicates that the system is in some self-trapped states. And for lambda equals to 2J, we see that the imbalance, that the system delocalizes, which is indicated by this zero imbalance in the steady state. So to quantify the degree of localization, we calculate the steady state imbalance, and we plot it as a function of lambda. And we see a clear transition from delocalized states to self-trapped states. And we do it for several values of system sizes. And this collapse basically indicates, and we ensure that the ratio, this total excitation NP divided by this total number of spins S is fixed. And this collapse says that this transition point is basically a function of NP by S. Yeah. Next, we also look at the system. Sorry. We look at the localization and the imbalance in the system when the system is in one of the eigenstates of the system. And we also compute the standard deviation in imbalance using this formula here. And we plotted this standard deviation versus imbalance. And each dot corresponds to a particular eigenstate of the system. And the top plot is for lambda equals to 2, and the bottom plot is for lambda equals to 10j. And immediately we see large differences between the two plots. On the top plot, we see that the imbalance just ranges from minus 0.04 to 0.04, whereas in the bottom plot, it goes from minus 1 to 1, which is in accordance to what we saw in the previous time dynamics plots. Next, moving on to chaos and integrability in the system, we use some diagnostic tools based on random matrix theory, where we compute something called the level spacing statistics, which is basically we take all the, we evaluate the eigenspectrum and we calculate the spacing between nearest neighbor levels, which gives me, and we calculate the distribution of these spacings. And then there is something defined as adjacent gap ratio, which is defined as such that minimum of Sn comma Sn minus 1 divided by maximum of Sn and Sn minus 1. Sn is the spacing. And we find its distribution. And we also calculate the spectral fall factor, which is defined as such. The reason we are doing such, we are calculating these things is because in quantum systems, when for systems which are chaotic, their distributions are given by Gaussian orthogonal ensemble distributions, whereas for systems which are integrable, the distributions are given by Poisson distributions. So this is a good diagnostic tool to categorize the quantum system into either chaotic or integrable. And this is the result what we get. On the left-hand side, we have the results for lambda equals 2j, right-hand side for lambda equals 10j. And we see that on the left-hand side, all the values, all the quantities agree with the GOV case, whereas on the right-hand side, all the quantities agree with the Poisson case, which says that lambda, this side is chaotic, this is integrable. Now, to exactly quantify this, how much it's chaotic, so one good estimate is this average adjacent gap ratio. And we know that we can calculate this, like for the Gaussian orthogonal ensemble, the average adjacent gap ratio is 0.536, whereas that for Poisson, it's 0.386. And if my systems, and I calculate it for my system for different system sizes here, and I see a clear transition from this GOV behavior to Poisson behavior. And we do it for different system sizes, increasing system sizes, and we do not see that this transition becoming any steeper. So it's no kind of finite size effect that we are seeing here. And for these intermediate values of lambda, we see some kind of a mixed behavior where the system is neither integrable, nor completely chaotic, nor neither completely integrable. Now, now that we are done with the quantum model, we can move on to the classical system. And the classical limit can be taken very simply, where we just replace the annihilation creation operators by position momentum operators and scale them by root over the total spin. And dealing with the spin variables, we scale all the spin variables by S and take S to infinity, and which leads us to a classical spin which lies on some sphere of radius half. And doing all this business leads to this Hamiltonian for a single Tavis Cummings monomer. And for the dimer, it just becomes something like this. And one thing to notice is that when we do these scalings for the variables, my energy scale like this, and so does my imbalance, which has the same dimensions as my energy. And so what we do is we consider an ensemble of initial states sampled all over this fixed excitation surface on the phase space. And this excitation we take is to be 2.5, because in the quantum case, we kept this ratio of total excitation by S to be 2.5. And since in the classical, we are scaling everything by S, so this has to be kept 2.5. And this ensures that we are comparing indeed oranges to oranges and not some oranges to apples. And then we calculate, and we then evolve the system using Hamiltonian equations. And Hamilton's equations, and then we calculate the mean in imbalance and the standard deviation in imbalance, and we again plot it for the two cases of lambda equals 2j and 10j. And this is a good point to remind ourselves about the quantum results. Yeah, and on the left-hand side we have the quantum plots, and this is the right-hand side with the classical points, classical plots. And we can see not just very good qualitative similarity between the structures, but also quantitative agreement between the numbers that we see here. It's also in terms of energies, we have ensured that the energies are almost in a similar window in both the cases. And we see a very good agreement between the quantum and the classical case. And if many of you might know about conjectures like the BGS conjecture, where they say that quantum classically chaotic systems have random metrics. Classically quantum systems, when you take the quantum limit and find their energy levels, they follow random matrix theory distributions. So these conjectures kind of give some correspondence between classical and the quantum systems. So we are seeing some kind of correspondence here in between in the context of imbalance here. But these plots, the chaotic behavior or the ergodicity of the system is not quite captured by these kind of data. So for that, we calculate Lyapunov. And we calculate Lyapunov using the Bennett's method. And for lambda equals to 2, you see that for different trajectories, all of them kind of, I have taken almost 100 trajectories here. And all of them kind of saturate to a single value, which indicates it's very close to ergodic. I can't say completely ergodic because there are some trajectories which differ in the steady state value. But for the case of I'll just wrap it up. For the case of lambda equals 10j, it's indeed far away from ergodic. Like I could only get 20 or 30 trajectories, and even in those trajectories, we see like they're completely scattered all over the places. The Lyapunov. So here there is complete absence of ergodicity, but here we do see some kind of ergodicity here. And this also indicates some kind of mixed phase space behavior where we can have some chaotic as well as regular trajectories. Since I'm over time, I'll just keep the summary window here, where I've just summarized all the results that we have done, and I'll be happy to take any questions that you have.
Could you go back to that diagnostic tool slide that you were saying?
Yeah, sure.
And could you perhaps give some intuition as to why they are good diagnostic tools? Because I'm not really aware.
So as I was saying, there's this conjecture by BGS, which says that for classically chaotic systems, when you take the quantum limit on it and quantize it and find the energy levels, they follow random matrix theory statistics. On the other hand, classically integrable systems follow Poisson statistics in the quantum side. So in the quantum model here, if I find these quantities defined, so level spacing, adjacent gap ratio, and all, and I find their distributions, if they agree with random matrix theory, it says that they are chaotic. On the other hand, if they agree with Poisson, it indicates that they're integrable. That's the intuition behind calculating these things.
Also, in addition, lambda equals 0 is a completely integrable thing?
Yeah, lambda equals 0, there's no interaction. You just have all you have is like some
individual.
Yeah, you just have this A dagger A and SZ. There's no interaction, nothing. And even with lambda non-zero, it's integrable. It's only when you put two such models together and you put some kinetic coupling between them, you can have regions where they are not integrable.
Yeah, I mean, two such models with lambda equals 0. What is that? Because if you go back to the curve that you had, the lambda varying from 2 to 10j, and you have plotted whether the distribution is this thing.
Yeah,
it seems to be going back in the, like, if you look at the 0 and 2 window, which is not in the axis, but
Yeah. So
I
the
think it's
reason
going
that we
back or
didn't put
something.
any zero close to zero window is mainly because in this region we get very spurious statistics, and so it's not the statistics that we get and do not quite indicate what actually it is here. But if you put lambda equals to zero, which I mean, even if for the dimer case, if I put lambda equals zero, I mean yeah, it's just a harmonic oscillator. Yeah, it's just coupled harmonic oscillator. You can exactly write down the solutions for it because the spin is completely decoupled. You don't have to worry about it at all. Yeah, it's you
Yeah.
can.
So basically, for small lambda or like lambda 0 and large lambda, it's integrable because the distribution also looks Poisson.
Yeah.
Okay.
Can I just ask one question? So all these computations are done with this maximal kind of spin sector? Or?
Yeah, I should have mentioned that I didn't, but yeah, all this computation is done with the maximum spin sector.
So
since we don't have any term that couples different spin sectors, so we can do that.
right. So if you start with, so that basically is the statement that you have sufficient energy in some sense, or like you start with it's like all excited states for the two level systems. Is that
all excited states?
Yeah. So now if you're in a different sector, do you think these integrability statements will be different?
I'm not sure. I haven't come across this model itself is defined in this way where we look at the maximal spin sector. Not looking at the maximum spin sector would lead to some other model which I haven't investigated, and I haven't seen any literature, so I'm not sure what will happen. Probably it's a good idea to check that out.
Any other questions? Okay, let's thank the speaker then.